microphone, so that forces me to speak louder. I think that's a good thing. I'm Pedro. I'm now a postdoc at Oxford. My talk's about the right kind of generic programming. So I added the emphasis there, because the idea is not to be read as the right kind of generic programming, but it's the right kind of generic programming. So the presentation, there's a lot of code in my slides, and I'm going to go through a lot of things, sometimes perhaps a bit too fast or a bit too slow, so just feel free to interrupt me at any moment with any questions you might have. So GHC 7.6 just came out last week or something like that. That's good. Now we have user-definable kinds by promotion. So we can define a data type, and this data type gets lifted to a kind automatically and its constructors to data types. We also get kind polymorphism, so that's another feature from the type level that is now lifted to the kind level. We have type level literals more or less, so there's support for type level naturals and symbols or strings if you wish, but they don't fully work yet. Perhaps they're a bit like kind polymorphism was in 7.4. They're kind of there but not really officially supported yet. And of course, as soon as you give people new features, you get new requests, because people start playing with the new features and they want more. So this talk's going to be about how we can use the new features to improve generic programming in GHC, and also how we can try to improve and fail, or at least I fail, at improving generic programming with the new features in some cases. So also feel free to interrupt me at any moment and say that no, you can do this better, or you can do this when I say that you can't. Because when I say that you can't, I mean that I can't. Maybe, of course, someone else can. Okay, let's delve into promotion. In the paper, you can find a standard example of natural numbers. Here we go straight into universes for generic programming. So let's say you want to define a representation of the structure of types as a data type. You can define a data type, call it universe. You can ignore this star for now, the argument. But you see that we have units that will encode for constructors without arguments. We have sums and products to encode choices between constructors and multiple arguments to constructors. We're going to have constants for things, I don't know, like integers, for instance. And we will use to encode recursion, so we put I is where you find recurrences of your data type. And we'll also be able to store some form of meta information, like constructor names, about your data types. So conceptually, if you want to encode lists, you would write a value of this type universe. So that would be something like a choice between unit for the empty list, or some integer together with a recursive call, and this would have type universe of, well, integers, because you want integers to be here, but then of course this has to be a specific int, not just integers in general. So as you can guess, this is all nonsense. This is not what we want. What we want is to change the colors. So I'm using colors to denote the different synthetic categories. So constructors, the value level, show up in blue. Types show up in orange. Also type variables show up in orange. And kinds show up in green, like star here. And promotion means that you're not just defining the data type universe, you're also defining the kind universe. And then that kind is inherited by these types here. So we can represent lists as a type now by using these promoted constructors, which are now types. So they appear in orange down here. And then you indeed have a choice between a unit or a constant with an integer. And why can we put int here? Because we essentiated our universe with the kind star. So since in our constants here we can have things of kind star. Well, int is of kind star, so that's what we want to have. So this is a representation for listed integers at the type level using promotion. This is basically encoding the universe of the regular library for generic programming, which is a library with a fixed point of view. So that's why you have this these promoted kinds, so the only kind, star is the kind of types that have values. All other kinds have types that do not have values. So if you want to have values, you need to have something of kind star. So to inhabit our generic universe, we need to define a GADT that is indexed over the universe. And this is going to give the inhabitants, indeed, of our representation. So unit is the only inhabitant for the interpretation of unit. For sums, here we'll have two inhabitants, left and right, whereas the left is an alpha and the right is a beta. For constants, we get an alpha for a k of alpha. And we carry around the contained thing in the universe, which is what we store in the I case. And for the meta information, we just add a class constraint, basically, that will later allow us to extract this information, like constructor names, etc. Now, the first thing that you notice here that I dislike particularly is that there are primes everywhere here. So there's U prime, for instance, I prime. Why? Because we've defined U and I already, and we've defined them as the constructors of this data type. That's completely useless to us. We never use universe as a data type. We only want it as a kind. So we're never interested in these guys as constructors. We're only interested in them as types. Nonetheless, they are constructors. They take up your namespace. So when you define the interpretation and you actually want to use the interesting names here, you can't. You have to give them another name. So this is one of the disadvantages of promotion, is that you have to define a data type to get the kind from it.
So can you define this as a type value?
This? Yeah. No, not really. You need to get hold of data to pattern match on and things like that.
Yeah.
I mean, I'm not so sure I can say that you need it, that you can't. Perhaps you could, right, by saying that this is interpreted as neither, and the product is maybe. I'd have to look at it. Anyway, going on with the annoyance of having the primes everywhere. Inhabitants, so the values of our generic representation of lists, are now values of this GADT type. And this is how you can encode the empty list, and this is how you can encode the list with a 0 and, well, more lists. So I'm just using like regular, one-level generic representation here. So in the recursive positions, you don't get representations of lists, but you get actual lists. The meta information, I kind of glossed over it until now. But we can also list all of this to the type level now. So we have a data type meta information for constructors, which is going to record the fixity of the constructor. What is this movement for? If it's a record, yeah, here is it. And a symbol is a built-in type now for literals at the type level. So then we have this class constructor that's going to be indexed over the name of the constructor, and from it we can get the constructor name, its fixity, and if it is a record. So this is basically the value level reflection of what this is. And remember that we're going to use the promoted version of this one, as you can see in the type of C. We're using it there as a type. This is more clear in an example, which I'll show soon. We have a regular class to embed, or to represent the embedding between data types and their representation. And the advantage of using our promotion mechanism now is that we can show that the pattern functor of a data type is not of kind star, or of kind star to star. It's really of kind universe. So it goes specifically and only can be represented by these sums and products that we define and nothing else. So in an example, you can see here how we encode lists in the regular library using this promotion. The meta information records at the type level. This is a type level string. It's not in orange because it's complicated to do that in LaTeX in my case. And also this 5, they are type level literals. a type level Boolean value. And the representation is actually here. So it's a unit or a product of a alpha and the recursive occurrence of the list again. The from and to conversion functions are mostly unchanged, apart from the primes everywhere. And then you see here this the instances for constructor. This is basically to mimic at the value level what you have at the type level. Javor, in his implementation of type level naturals and literals, actually has a mechanism to do this already, because this is something that you often want to get from the type level back to the value level. So, this is cool, and it all works, apart from the annoyance with the names, etc. So I'm happy. Now, something else that works is how you can improve the typeable library using kind polymorphism. The current situation is that, so if you know typeable, this is to have at runtime a type representation of your values so that you can, for instance, do runtime comparison of types and casting, safe casting, if you need it. Right now there are 8 typeable classes, 1 for types of kind star, and then 7 others for higher kinds up until star, 7 times. We need this because you often want to, it is really different to compare the type maybe with the type maybe alpha for some particular alpha. So for types of higher kinds, like maybe, you need 2 instances, one for typeable 1, and the other one for typeable that depends on the typeable for the parameter as well. With kind polymorphism, we can define a single kind polymorphic typeable class. So here you take some type whose kind is not necessarily star. It's some kind of kappa. Did actually Proxy before. So Proxy is the sorry. This is the definition of proxy. I went over it. This is just a type that if you need to just represent at the type level something, you just encode it there and the value you don't care about. It's kind polymorphic, so this guy doesn't have to be of kind star. Sorry. We need that here because, well, this variable by the class restriction has to appear somewhere in the method. But since it's not a kind star, we don't just use it as a value, so we just use a proxy representation for it, and then associate the type representation. And now we can give a single kind polymorphic instance for the applied types. If we have something of kind K1 to K2 and something of kind K1, then we can apply them to each other, and this gives our towers or applications for higher kinds in one go. And then we can keep for backwards compatibility the old methods type of and type of 1 by just calling this the kind polymorphic type ref with the appropriate proxy type. So this all works, that's good. Now, the problem that I tried to solve next was how to get rid of the same duplication that is showing up in SYB. So SYB relies on typeable to perform cast at runtime for the extension mechanism, because you want to be able to define a function that has a general case to be applied in, let's say, most cases, but then a special case for the type maybe of integers, and yet another special case for the type maybe of yet anything else. So this is relying on typeable. And you can imagine that this guy is relying on basically the type of 1 stuff because it only looks at maybe, whereas this one is relying on the type of, or the typeable instance of maybe, because it does depend on the actual thing that is inside, containing the maybe. And SYB, kind of like typeable, mimics this duplication, and in these primitive extension functions, there are a couple of them for higher kinds. So what I wanted to do is also to get rid of that. In more or less the same way we got rid of it in typeable. So these are the extension functions. You can see that x0 relies on typeable and x1 relies on typeable 1. And what they're doing basically is taking a default case and the possible extension. If you manage to cast the extension, so if the value that you get matches the one with the extension, you use that. If not, you use the default case. And they're exactly the same, apart from one using gcast and the other one using datacast1. Datacast1 comes from the data class and has a default definition that just says nothing, so don't do any casting, which is appropriate for things of kind star. But if you are giving an instance of data for maybe, then you have to redefine datacast1 to be gcast1, which we'll see next. Gcast, that's the one that's used for x0, is just using type of to compare the type to the cast if necessary. Gcast1, on the other hand, is using type of 1. Other than that, it's exactly the same as gcast. So this duplication is creeping into SYB because you're forced to give this datacast 1, 2, etc. instances for types of higher kinds. Can we get rid of this? So it is relatively simple to define a kind polymorphic gcast. We just abstract over the kinds, over the result kinds here, and also the containers around them. And all the rest looks basically the same. You use now typeref, the kind polymorphic function from Typelevel. This is just a trick to get the right type out. And you can define the ext function now to be general, so not 0 or 1, but to work on all kinds. But, so the example we had before can now be written like this, using only ext in both cases. And here we say for maybe int we return 1, and for maybe in general we return 2. But this is not good. I mean, this works in this particular specific simple example, but not in general, because what I'm doing here is using a thing of kind star to star in my type. That's fine if I'm not inspecting the values. But in general, you want to inspect this value. So think of the generic show function. You want to have a general case. You want to have a case for lists in particular, because they have special syntax. And you want to have yet another case for lists of characters, because they have an even more special syntax. But you have to inspect the values there, because you have to show them. So if you try that there, you're going to, for the general list case, you're going to be stuck with a list, whereas you want a list of alphas for some alpha. To actually get a value, you need it to be the kind star. And I don't know how to do that. I think I try things like, I don't know, having a type family that comes up with values and just apply this thing so that you can actually get a value out of it. But no, I didn't succeed. So, I don't know. Going on with something else that works, at least for a while. I added support for generic programming in GHC a while ago, using type families in a way similar to instant generics, in a library called Generic Deriving. This looks again a bit like regular. There's a class, generic, that for some type alpha you can get a representation out of it. The representation is of kind star to star because we always abstract over one parameter, so that you can do things like map. And you have from and to functions. But we need two type classes because you want to do things like map, and you have to have special support for lists and maybes, so those will need to get an instance of generic 1 as well. So we try to do our best to remove duplication there, and the representation of the universe is not duplicated, but you still need these two classes. So can we perhaps, and of course you only support one parameter, so you want in general to support multiple parameters. How do we do that? Can we use type polymorphism there? So the first idea I had was to encode not only the representation of the type, but also the arguments associated with that type. So this guy will give you a list of things of kind star, which are basically the type variables of the type alpha. And then in your interpretation of the universe, you will also get these parameters around so that you can use them in the representation. this. So the only interesting case now is the addition of a parameter representation with a natural, which says I am the parameter number 1 or I am the parameter number 3. And in the interpretation for these parameters, we just we have this list of types, or we just get the nth out of it from where the n is given by the representation. We need a type level lookup function on lists that you can define more or less. Now, this doesn't work. So first, the small annoyance is that you can't really define this safely because we're using lists of types, but in fact we know statically how many parameters a type has. So we could instead use vectors so that we have a fixed length and then the lookup can be safe. But we can't use vectors because vectors in Haskell are defined as GETs, and we are relying on the promotion of these guys to the kind level, and there is no promotion of GETs. So we have to use lists and live with the unsafety there. But more problematic is composition. When you have only one parameter, it's clear how you can compose code. So you can have, for instance, trees of lists of alphas, and you can still map over this because you represent this as a composition and you map over the composition. It's all fine. But if you generalize this to multiple parameters, then it's not clear anymore how you can do this, because imagine you try to compose lists with either. So you need to have a more fine-grained control over how to connect these inputs to the outputs, let's say.
Can I ask a question on the first one? So, when also check the definition of vectors, we use a type family, so just send 0 to the type, a successor to a pair that occurs. And then you would need GATs. I think that might work.
Say again?
So instead of defining vectors as a GAT, you define the type of vec AN as a type family, which computes for any n nested two.
Then you want to promote a type family.
Yeah, okay. An alpha load method.
I think you'll get into the same problem.
Okay.
So yeah, I think this won't work. It would be nice if it would work because it's relatively simple and similar to what is already there, but I think it won't work. So in the paper, I go about how you can handle this by using, so say, a completely different representation that is more explicit about inputs and outputs in the universe. I don't have time to talk about that here. But the idea is that you can have a universe with even functions inside it, an existential quantification. And this is all happily promoted by Teach to the kind level. This all works. Having interpretation, it's a bit complicated, but it all works. And previously this was only possible in Angular, basically. You can encode lists, and you can encode rows trees that use lists, using composition there, and map works, everything's fine. And then I have an example of something that doesn't work, is when you, because you have this explicit notion of inputs and outputs, sometimes you need to say what inputs map to what outputs, so there's an operation called re-indexing. And there you need to use type families, because you have these functions at the value level that you need lifted at the type level, so you use type families, but I can't get them to work due to restrictions on type family saturation. But you can read more about that in the paper. So, conclusions. It's great to have these new features, and they can really help us a lot in making our generic programming libraries more safe and more precise, or even making some things that weren't possible before now possible. But we want more. In particular, we want to be able to define kind without having to define the data type. It shouldn't be too hard. It's a bit of a syntactic thing to agree on how you want to denote these things. We want kind synonyms. We don't have kind synonyms. This is again also just a small limitation. You should promote probably type synonyms directly to the kind synonyms as well. The type level naturals, the symbols, they're there, but there are no solvers for it yet. So if you have things like 1 + 1 or 1 + 2 and 2 + 1, they are not known to be the same because there's nothing solving these equations. And I think the same applies for symbols, so you don't have things like pen equality on your names at the type level. We mean those. It would be good if we can check for exhaustiveness of instances, because when you're giving now, when you're defining a generic function, you define it over promoted data types, so you know exactly how many constructors there are, which means you know exactly how many types there are, so you know exactly how many instances you have to give, and if you miss one, the compiler could warn you that you're missing the instance for some or something like that. Promoted GDTs, we'd like to have that so that we can have these vectors at the type or at the kind level. The saturated type family application, which we need to actually make use of the promoted functions, because then you need to have functions at the type level and you need a pattern. Future work, so more things that I looked at and I'm not entirely sure you can do. Any removal duplication in left M2 and zip width 3. So this paper on arity generic data type generic programming. You can do this, yes, it's all been done in Angular, I think. It's quite a lot of work, and I tried to do it in Haskell in a relatively simple way, so without having to involve the kinds themselves directly. But I failed, so maybe you actually have to do it in the way it's been done there. And I'm not sure even that is possible. The reindexing, so this goes back to the unsaturated type family applications. And I have no idea if performance is affected by the use of types. I didn't look at this, but yeah, I should. That's future work. Thank you for your attention.
Last year, so I will be the discussant. Okay, thank you, Anders.
Thank you, Pedro, for a lovely paper and a lovely presentation. So, this is a quite subtle paper, and I really enjoyed reading it, actually. It's talking a lot about type families and the data kinds that you now have in GHC. And what's interesting, what I find really interesting, at least, is if you read the original papers, and everyone knows the example of having vectors where you don't need to define natural numbers in this funny type of thing. So that's something that works. But then once you really want to use it for something, you run into interesting problems. So that's why it's good to have this concept. And I think the problems that you ran into, some are just like the implementations and things about the Typelevel constant, for example. That's just the implementation that actually needs to be finished, and having special kind syntax. You need to define the syntax. A little bit more, but it's not a kind of fundamental flaw. The things which I found more interesting were to see the real problems that we ran into, like not having Typelevel GPTs, which is also a problem if you want to do kind of dependent type programming in this style. So there's a paper in Haskell Symposium, I think, about Stephanie. Okay, great. About the singleton library, where they run into exactly the same problem, not being able to have GPTs means that you are limited in what you can do. So, one thing I really liked is I like what makes this paper very special, I think, is that it's clear that Pedro knows a lot about the different kinds of generic libraries. I mean, he knows everything from extracted boilerplate to he's implemented his own libraries to regular and multivariate and so forth. And he's also working on his kind extensions, so he really knows what he's talking about. And so in the beginning, Pedro mentioned that the way he'd like to pronounce the title of the talk would be the right kind of generic program. But the alternative pronunciation would be the right kind of generic program. And the question, which isn't really explicitly asked in the paper, but which you can kind of reading it, you start to wonder, is you see there's a very big difference between these different approaches. That's scrap your boilerplate versus constructing an explicit language. It's a completely different style of generic programming. One thing which, doing this kind of study, is seeing how new features make it easier or make these different styles of generic programming easier to use or nicer to use or something of the kind, so you can do fancy tricks, is to see what kind of results you can get against these different libraries, how they improve. And the feeling I got is that kind of the universe stuff, where you have explicit representations of your data, that works much better. It profits much more from having never really liked scrappy boilerplate. I always thought it's so I think Connor said something like it works despite of the structures and using the structures, right? And this is a kind of a case in point where you can say you have all this nice new technology, you have all these nice generic libraries, and they'll kind of blossom because we have these new data kinds and wonderful things we can do, even more generic stuff. But scrap your boilerplate, you kind of Pedro knows what he's talking about.
It's the most popular library.
Live, right? And kind of, if you take a step back and try to put this more into the broader context, a lot of the work which is going into GXC is about kind of pushing it more and more towards the memory. And you can see that that now you can now do things like the index stuff, which previously you do in ACTA, you can now do that in this one. So that's really good. And but it also, I know that you have also used dependent method, which is like find a relation between these things, right? And study them. And then actually prove properties about various embeddings. And that's the kind of stuff that you still can do despite having all these kinds of things. So I think this is a really interesting thing. And I welcome further discussion. Thank you very much. Good to go back to the picture.
Well,
yeah.
I can do it. Yeah.
So can I respond a little bit?
Yeah, sure.
Some of the stuff that Whoever said. So I just want to talk a little bit about this slide, and you were talking a little bit about sort of some of the stuff that's easy, that's just a lot of syntax, and Pedro mentioned that too, and some of the stuff that's harder, right, a more difficult challenge. So in terms of promoting GATs or having type families at the kind level, I just wanted to point out that Richard and I and a student Justin, we've been looking at this problem of how to have kind equalities. And we've worked it out in the context of Haskell's intermediate language FC. So we have some progress there. We have a draft paper on that. So if you're interested in how that might work out, and so there's reason to also be positive that this might show up in Haskell, right? So that's good. And I really hope that this comes out.
I don't want to slam your work in it.
No. I wanted to be positive in that direction, and I really like Pedro's paper because it points out just why we really need this thing. But and then the second point is this unsaturated type family application, and that I think is even more interesting. That's restriction, because this is like a real fundamental difference between sort of the point of view of Agda and the point of view of Haskell, right? Because this falls out because of type inference, right? Haskell limits this type family saturation just for, to be clear nice with the homogamous normal type inference, right? Down at the FC level, it doesn't have to be there, right? So Haskell is working on maintaining this principal types property, and I would really like, and I don't want it to give that up, right? I think Haskell would really lose something if it gave up its principal type property. I would really like to see if there was a way we could have unsaturated type families in a way and still have principal types. And that, I think, is a real challenge. Yeah.
Come talk with me at the break.
Break.
You don't want to share it with us?
Second half day. On type inference for languages of type level leftists.
Excellent.
Okay. Yeah, Jeremy?
I had a very formative experience at the workshop on generic programming in 2000, which was co-located with NDC in Portugal. I think we had a hot topic session there, and I took my life in my hands and stood up and said, there's all these things that I'd like to do with nested data types, and I can't really encode them properly. How can I get this? And Randy Pollock stuck his hand up and said, you need to use dependent types. And then I said something else about, I think it was about folds and unfolds and properly encoding recursion and co-recursion and the termination properties and so on, how do I do this? Randy Pollock stuck his hand up and said, what you need is dependent types. And it's taken me 12 years, but I'm coming to believe in what he says. I can't help feeling that this is, I mean, we're struggling towards that here, but this feels like a an attempt to force things that don't go properly, and just sitting there on the side and neglected and underappreciated is more and more appreciated, of course. We still feel the need to take dependent type features and force them into a non-dependent type language. I just wonder if this is the right way of doing stuff. Maybe I'm the one sticking my hand up now, 12 years later, saying what we need is dependent types.
But are you willing to give up on principal types?
I'm not perhaps the right person to ask, because as soon as my program type checks, I never need to run it. But I think maybe I'm the right program person to ask, but type checking is I don't actually run my program.
Yeah, that's a duality, right? We're now basically duplicating things at the type level, and we want to promote a GDT, so we're duplicating things at the kind level. And how much more do you want to go? You could just, go dependent all the way. All the way. But I think Stephanie's also talking about this in her draft paper, so this is a hot topic.
Yeah. Connor and I have been talking about how we could put in a real pi into Haskell, so they don't have to have the duplication of the single things. But I should also say before that's all like pi abstract stuff. So, but
don't distract him from getting epigram working.
And there's also the other direction, right? I mean, there's this duplication, but in the beginning you have shown this universe where you have the star parameter, and there is also there is a mismatch. Sometimes you would like to define something only as a kind, but alternatively you could also sometimes say what you'd actually like is to have star as a type, where it is only a kind. So if you start making things more similar, you get this feeling that well, in a way they are very similar, but not quite, and it always feels very complicated due to that.
Done with kind.
Draft paper, we have start. So
Yes, we'll just insert we have a draft paper after every. One more.
With respect to the issue you faced when trying to sort of upgrade the exe function for XMP, you had this maybe of kind of star, but you needed to expect its values. Would it suffice if you had a way to take a star type and sort of saturate it with for alls?
Yeah, that's what I tried.
So how did you try that? Did you use a data family?
Yeah, I used the type family.
So can you have for alls on the right hand side of the type family?
No. That's like failed.
Okay, so you just, that was your thing.
Of course, to do that, you could, in data families, you can have these for alls, but then there are existential,
Yeah, it gets messy.
then you have constructors in the way.
It just reminds me of something I saw in like polytypic functions out of polynomial types.
Yeah.
yes, definitely.
Okay. So is that?
Yeah, but then you
Is
then
it,
you
is
really
it putting out a draft paper on this?
no, that's
We're
all
all
done.
right.
I mean, the RT generic, the type generic.
But in
Paper
Haskell,
does
I
it.
suppose is my question.
Yeah, so I think perhaps I should try that to just encode the kinds also, and then to do these things kind index. But I'm not sure.
I think I actually tried this one, some failed. But then again, GXC changes every week, so.